Ever contemplate what lies beyond the stars? What if the answer is, well, more stars, infinitely? Let's delve into the intriguing concept of an infinite universe. Picture the cosmos not as a finite sphere with a tangible boundary, but rather as an expanse that extends forever in all directions. This idea may seem mind-boggling, but it's a concept that has been proposed by scientists for centuries. Our universe doesn't have a physical edge you can touch or see. Instead, it has an apparent edge, which we call the cosmological horizon. This horizon represents the farthest point we can see in the universe. It's not a physical barrier, but one defined by the speed of light. You see, light travels at a constant speed, and thus it takes time for light to reach us from distant galaxies. The universe is about 13.8 billion years old, so we can see light from galaxies that are up to 13.8 billion light years away. This is our observable universe, our cosmic picket fence, if you will. But what lies beyond this picket fence? Well, given the theory of an infinite universe, it's quite simple. More universe. However, this is where things get a bit tricky. The light from galaxies beyond our cosmological horizon hasn't had enough time to reach us yet. Therefore, while we theoretically know there's more universe out there, we can't observe it. It's a bit like knowing there's a whole world outside your window, but the blinds are drawn and you can't peek outside. So we exist within a cosmic picket fence, our view limited yet surrounded by an infinite expanse of universe. Quite the peculiar situation, isn't it? But as we delve deeper, you'll find that the universe is full of such oddities and peculiarities, each one more fascinating than the last. Imagine a beach ball, a sheet of paper, and a Pringle. Now, what if I told you these could represent possible shapes of our universe? This might sound a little odd at first, but let's delve into it. Albert Einstein's general theory of relativity gives us three potential models for the shape of the universe. Each model is defined by its curvature, positive, negative, or flat. Let's begin with positive curvature. Picture a beach ball. This model suggests a finite, self-contained universe. But what's fascinating is that if you were to set off in a spaceship and travel in a straight line, you'd eventually end up right back where you started, much like circumnavigating the globe. However, current scientific evidence doesn't quite support this beach ball universe. Instead, our universe appears to resemble the other two shapes, a sheet of paper or a Pringle. Now imagine unrolling a massive sheet of paper that extends infinitely in all directions. This represents a flat universe. In this model, light travels in straight lines, and parallel lines will never meet. The idea of an infinite universe can be mind-boggling, but it's what our best observations currently suggest. But there's another possibility. What if we live in a universe with negative curvature? For this, think of a Pringle or a saddle. In a negatively curved universe, space is infinite, but it bends outward. Here, light would follow curved paths and parallel lines would diverge from each other. It's crucial to remember that these shapes are not literal. They are ways for us to conceptualize something incredibly complex and vast. They help us grapple with the idea of infinity and the nature of space itself. So our infinite universe could be either flat, like an unending sheet of paper, or saddle-shaped, like an infinite Pringle. In either case, we find ourselves in a universe that is unending and unfathomably large, a testament to the grandeur of the cosmos. How do you begin to comprehend the incomprehensible with the right mathematical tools, of course? Imagine the universe as a vast, infinite expanse. It's colossal, it's bewildering, it's, well, infinite. How can we possibly hope to understand something so boundless? Enter Penrose diagrams and conformal compactifications. Penrose diagrams, named after the brilliant mathematician Sir Roger Penrose, help us visualize and understand the structure of space-time in the universe. They're a bit like a map, simplifying the complex geometry of the universe into a two-dimensional diagram. This allows us to see the overall structure of the universe at a glance, including the paths of light rays and the event horizons of black holes. But what about the infinite? Surely we can't cram something infinite into a finite two-dimensional diagram. Here's where conformal compactifications step in. This mathematical technique allows us to compactify or encapsulate the infinite universe into a finite space. It's like folding up an infinitely long piece of paper into a neat, compact package. This process doesn't distort or lose any of the important features of the universe. It's a bit like how a globe represents the Earth. Sure, the Earth isn't really a small, holdable sphere, but the globe still gives us a good idea of what the Earth looks like and how its various parts relate to each other. In the same way, conformal compactifications allow us to see the overall structure of the universe. They help us understand the universe's cosmic horizons and the vast unobservable regions beyond our cosmic picket fence. In essence, we've wrestled infinity into comprehensible finite diagrams, a triumph of human ingenuity. Is our universe really 3D, or could it be just a holographic projection? Now that's a question that could trip up even the most astute amongst us. But don't worry, science has a way to grapple with it. Enter the holographic principle. This fascinating and somewhat mind-bending concept suggests that all the information contained within a given volume of space can actually be represented on a boundary to that space. To visualize this, consider a simple example. Imagine a room filled with objects of various shapes, sizes, and colors. Now, according to the holographic principle, all the information about these objects, their positions, their textures, their colors, could be encoded on the walls of the room. The walls would serve as the boundary to the room's volume. But how does this apply to our universe? This is where anti-de Sitter spaces come into play. These are mathematical constructs that describe a specific type of space-time geometry. Anti-de Sitter spaces are fascinating because they have boundaries that can act as holographic projections of the bulk or the interior of the space. So if our universe is an anti-de Sitter space, then everything we perceive as three-dimensional, the galaxies, the stars, the planets, and even us, could be just a holographic projection from a boundary of our universe. This might sound like pure science fiction, but it's a theory taken very seriously in the world of theoretical physics. It's a radical way of looking at our universe where the three dimensions we perceive are just an illusion, a hologram projected from a two-dimensional boundary. This doesn't mean our experiences or our existence are any less real. Instead, it gives us a new way to understand the fundamental nature of reality and our place within it. It's a challenging concept, but one that broadens our perspective and deepens our appreciation of the beauty and complexity of the universe. So we might just be living in an impressive cosmic hologram. How does compactifying the universe's infinite spaces into finite models help us? A question that brings us to the heart of conformal compactifications and their implications. Let's delve into the depth of this query. These mathematical transformations have a significant role in linking theories of quantum gravity with quantum field theory. The bridge between these theories is known as the ADS-CFT correspondence. But what does this correspondence mean? The ADS-CFT correspondence is a conjecture about a relationship between two types of physical theories. On one side of the correspondence, we have anti-de Sitter space, which is used in models of quantum gravity. This space describes a universe filled with negative dark energy. On the other side, we have conformal field theory, a type of quantum field theory that describes particles and their interactions. By compactifying the infinite spaces of the universe into finite models, we can illustrate the ADS-CFT correspondence. It's like turning a complex, sprawling novel into a concise, comprehensible summary. This approach allows us to tackle the seemingly insurmountable challenge of infinity, making it manageable and understandable. Through this transformation, lower-dimensional quantum fields can encode a higher-dimensional universe's gravity and contents. This is a profound concept that alters our perception of reality. It's as if we're living in a hologram, where a flat two-dimensional surface contains all the information necessary to project a three-dimensional image. This idea might sound like something out of a science fiction novel, but it's grounded in the complex mathematics of theoretical physics. It's a testament to the power of human ingenuity and our relentless pursuit of understanding the cosmos. So, even in its vastness, the universe might just be a coded message waiting to be deciphered. This statement captures the essence of conformal compactifications and their implications. It reminds us that the universe, in all its complexity and grandeur, might be understood through the language of mathematics, providing a tantalizing glimpse into the mysteries of the cosmos. So, what have we learned about our potentially infinite universe? Well, we've discovered that the concept of boundaries in an infinite universe is not as straightforward as one might think. Despite the common assertion that an infinite universe has no edge, it's possible to define mathematical boundaries. Like the particle horizon of the observable universe, these boundaries help us grasp the immense, unobservable regions beyond our cosmic picket fence, lending a sense of scale and relativity to our existence within the universe. We've also delved into the concept of multiple universes. Drawing from Einstein's general theory of relativity, we've explored the properties and implications of living in universes that can be closed, flat, or negatively curved. We've paid particular attention to the last two types, which are theoretically infinite. It's a mind-bending exercise, but it helps us understand the vastness of the cosmos and our place in it. In the pursuit of comprehending this seeming infinity, we've looked at mathematical tools like Penrose diagrams and conformal compactifications. These techniques help us manage the infinities at the universe's boundaries, making calculations possible. They provide a way to visually and mathematically understand the vastness of the universe by compactifying an infinite space into a finite diagram. Our journey also introduced us to complex theories like the holographic principle, which suggests that all information within a volume of space can be represented on a boundary to that space. We've seen how anti-de Sitter spaces and their boundaries act like holographic projections of the universe's bulk, adding yet another layer of intrigue to our understanding of the cosmos. Lastly, we've explored the implications of conformal compactifications. By mapping the universe's infinite spaces into finite, manageable models, these mathematical transformations not only help us understand cosmic horizons, but they also link theories of quantum gravity with quantum field theory through the ADIS-CFT correspondence. This shows how lower dimensional quantum fields can encode a higher dimensional universe's gravity and contents. Though we may never fully grasp the universe's entirety, we are forever inching closer to the truth, one theory at a time.